Plutonium, symbol capital P lowercase u, atomic number or element 94, is a rare transuranic radioactive element. It is an actinide metal of silvery white appearance that tarnishes when exposed to air, forming a dull coating when oxidized. The element normally exhibits 6 allotrops and 4 oxidation states. It reacts with carbon, halogens, nitrogen, and silicon. When exposed to moist air, it forms oxides and hydrides that expand the sample up to 70% in volume, which in turn flake off as a powder that can spontaneously ignite. It is also a radioactive poison that accumulates in bone marrow. These and other properties make the handling of plutonium dangerous, although its overall toxicity is sometimes overstated. The most important isotope of plutonium is plutonium-239, with a half-life of 24,100 years. Plutonium-239 is fissile, meaning that the nuclei of its atoms can break apart by being bombarded by slow-moving neutrons, releasing energy, gamma radiation, and more neutrons. It can therefore sustain a nuclear chain reaction after reaching a critical mass, leading to applications in nuclear weapons and use in some nuclear reactors. The most stable isotope of plutonium is plutonium-244, with a half-life of about 80 million years, long enough to be found in trace quantities in nature. Plutonium-238 has a half-life of 88 years and emits alpha particles. It is a heat source in radioisotope thermoelectric generators, which are used to power some spacecraft. Plutonium-240 has a high rate of spontaneous fission, raising the background neutron rate of any sample it is contained in. The presence of plutonium-240 ends up limiting a sample's weapon and power potential and determining its grade. Weapons, less than 7%, fuel, 7 to 19%, and reactor grade, greater than 19%. Plutonium-238 and plutonium-239 are synthesized by bombarding uranium-238 with deuterions and neutrons, respectively. Element 94 was first synthesized in 1940 by a team led by Glenn T. Seaborg and Edwin McMillan at the University of California, Berkeley Laboratories. McMillan named the new elements after Pluto, and Seaborg suggested the symbol Pu as a joke. Trace amounts of plutonium were subsequently discovered in nature. Discovery of plutonium became a classified part of the Manhattan Project to develop an atomic bomb during World War II. The first nuclear test, Trinity, July 1945, and the second atomic bomb used to destroy a city, Nagasaki, Japan, in August 1945, Fat Man, both had cores of plutonium-239. Human radiation experiments studying plutonium were conducted without informed consent, and a number of criticality accidents, some lethal, occurred during and after the war. Disposal of plutonium waste from nuclear power plants and dismantled nuclear weapons built during the Cold War is a major nuclear proliferation, health, and environmental concern. Other sources of plutonium in the environment are fallout from numerous above-ground nuclear tests, now banned, and several nuclear accidents. Section 1. Characteristics. Section 1.1. Physical. Plutonium, like most metals, has a bright silvery appearance at first, much like nickel, but it oxidizes very quickly to a dull gray, although yellow and olive green are also reported. At room temperature, plutonium is in its alpha form. This, the most common structural form of the element, or allotrope, is about as hard and brittle as gray cast iron, unless it is alloyed with other metals to make it soft and ductile. Unlike most metals, it is not a good conductor of heat or electricity. It has a low melting point of 640 degrees Celsius and an unusually high boiling point of 3,327 degrees Celsius. Alpha particle emission, which is the release of high-energy helium nuclei, is the most common form of radiation given off by plutonium. Heat given off by the release of and deceleration of these alpha particles make a mass of plutonium the size of a softball warm to the touch, while a somewhat larger mass can boil a liter of water in a few minutes, although this varies with isotopic composition. Resistivity is a measure of how strongly a material opposes the flow of electric current. The resistivity of plutonium at room temperature is very high for a metal, and it gets even higher with lower temperatures, which is unusual for metals. This trend continues down to 100 Kelvin, below which resistivity rapidly decreases for fresh samples. Resistivity then begins to increase with time at around 20 Kelvin due to radiation damage, and the rate dictated by the isotopic composition of the sample. Due to self-irradiation, a sample of plutonium fatigues throughout its crystal structure, meaning the ordered arrangement of its atoms becomes disrupted by radiation with time. However, self-irradiation can also lead to annealing, which counteracts some of the fatigue effects as the temperature increases above 100 Kelvin. Section 1.2 Allotrops. See also the main article, Allotropes of Plutonium. Plutonium normally has 6 allotropes and forms a 7th, zeta, at high temperature within a limited pressure range. These allotropes, which are different structural modifications or forms of an element, have very similar internal energies, but significantly varying densities and crystal structures. This makes plutonium very sensitive to changes in temperature, pressure, or chemistry, and allows for dramatic volume changes following phase transitions from one allotropic form to another. Unlike most materials, plutonium increases in density when it melts by about 2.5%, but the liquid metal exhibits a linear decrease in density with temperature. Densities of the different allotropes vary from 16.00 grams per cubic centimeter to 19.86 grams per cubic centimeter. The presence of these many allotropes makes machining plutonium very difficult, as it changes state very readily. For example, the alpha form exists at room temperature in unalloyed plutonium. It has machining characteristics similar to cast iron, but changes to the plastic and malleable beta form at slightly higher temperatures. The reasons for the complicated phase diagram are not entirely understood. The alpha form has low symmetry monoclinic structure, hence its brittleness, strength, compressibility, and poor conductivity. Plutonium in the delta form normally exists in the 310 degrees Celsius to 452 degrees Celsius range, but it is stable at room temperature when alloyed with a small percentage of gallium, aluminum, or cerium, enhancing workability and allowing it to be welded. The delta form has more typical metallic character and is roughly as strong and as malleable as aluminum. Section 1.3 Nuclear Fission. Plutonium is a radioactive actinide metal whose isotope, plutonium-239, is one of the 3 primary fissile isotopes. Uranium-233 and uranium-235 are the other 2. Plutonium-241 is also highly fissile. To be considered fissile, an isotope's atomic nucleus must be able to break apart, or fission, when struck by a slow-moving neutron, and to release enough additional neutrons in the process to sustain the nuclear chain reaction by splitting further nuclei. Plutonium-239 has a multiplication factor larger than 1, which means that if the metal is present in sufficient mass and with appropriate geometry, for example, a compressed sphere, it can form a critical mass. During fission, a fraction of the binding energy which holds the nucleus together is released as a large amount of thermal, electromagnetic, and kinetic energy. A kilogram of plutonium-239 can produce an explosion equivalent to 20,000 tons of TNT. It is this energy that makes plutonium-239 useful in nuclear weapons and reactors. The presence of the isotope plutonium-240 in a sample limits its nuclear bomb potential, as plutonium-240 has a relatively high spontaneous fission rate, approximately 440 fissions per second per gram, or over 1,000 neutrons per second per gram, raising the background neutron levels and thus increasing the risk of pre-detonation. Plutonium is identified as either weapon grade, fuel grade, or power reactor grade based on the percentage of plutonium-240 that it contains. Weapons-grade plutonium contains less than 7% plutonium-240. Fuel-grade plutonium contains from 7 to less than 19%, and power reactor grade contains 19% or more plutonium-240. The isotope plutonium-238 is not fissile, but can undergo nuclear fission easily with fast neutrons as well as alpha decay. Section 1.4, Isotopes and Synthesis. See also the main article, Isotopes of Plutonium. 20 radioactive isotopes of plutonium have been characterized. The longest lived are plutonium-244, with a half-life of 80.8 million years, plutonium-242, with a half-life of 373,300 years, and plutonium-239, with a half-life of 24,110 years. All of the remaining radioactive isotopes have half-lives that are less than 7,000 years. This element also has 8 metastable states, though none are stable, and all have half-lives less than 1 second. The isotopes of plutonium range in mass number from 228 to 247. The primary decay modes of isotopes with mass numbers lower than the most stable isotope plutonium-244 are spontaneous fission and alpha emission, mostly forming uranium, 92 protons, and neptunium, 93 protons, isotopes as decay products, neglecting the wide range of daughter nuclei created by fission process. The primary decay mode for isotopes with mass numbers higher than plutonium-244 is beta emission, mostly forming americium, 95 proton isotopes, as decay products. Plutonium-241 is the parent isotope of the neptunium decay series, decaying to americium-241 via beta or electron emission. Plutonium-238 and plutonium-239 are the most widely synthesized isotopes. Plutonium-239 is synthesized via the following reaction using uranium and neutrons via beta decay with neptunium as an intermediate. Uranium-238 plus 1 neutron yields uranium-239 plus a beta particle, which yields neptunium-239 plus a beta particle, which yields plutonium-239. In other words, neutrons from the fission of uranium-235 are captured by uranium-238 nuclei to form uranium-239. A beta decay converts a neutron into a proton to form neptunium-239, half-life 2.36 days, and another beta decay forms plutonium-239. Workers on the Tube Alloys project had predicted this reaction theoretically in 1940. Plutonium-238 is synthesized by bombarding uranium-238 with deuterions, D, the nuclei of heavy hydrogen, in the following reaction. Uranium-238 plus deuterium yields neptunium-238 plus 2 neutrons, Neptunium-238 beta decays to plutonium-238. In this equation, the deuterium hitting uranium-238 produces 2 neutrons and Neptunium-238. The Neptunium-238 spontaneously decays by emitting negative beta particles to form plutonium-238. Section 1.5, Compounds and Chemistry. See also the main article, Plutonium Compounds. At room temperature, pure plutonium is silvery in color but gains a tarnish when oxidized. The element displays 4 common ionic oxidation states in aqueous solution and 1 rare one. Plutonium-3 is a blue lavender. Plutonium-4 is a yellow-brown. Plutonium-5 is pink. Plutonium-6 is pink-orange. Plutonium-7 is green. This heptavalent ion is rare. The color shown by plutonium solutions depends on both the oxidation state and the nature of the acid anion. It is the acid anion that influences the degree of complexing, how atoms connect to a central atom, of the plutonium species. Metallic plutonium is produced by reacting plutonium-4 fluoride with barium, calcium, or lithium at 1200 degrees Celsius. It is attacked by acids, oxygen, and steam, but not by alkalis, and dissolves easily in concentrated hydrochloric, hydroiodic, and perchloric acids. Molten metal must be kept in a vacuum or an inert atmosphere to avoid reaction with air. At 135 degrees Celsius, the metal will ignite in air and will explode if placed in carbon tetrachloride. Plutonium is a reactive metal. In moist air or moist argon, the metal oxidizes rapidly, producing a mixture of oxides and hydrides. If the metal is exposed long enough to a limited amount of water vapor, a powdery surface coating of plutonium dioxide is formed. Also formed is plutonium hydride, but an excess of water vapor forms only plutonium dioxide. With this coating, the metal is pyrophoric, meaning it can ignite spontaneously, so plutonium metal is usually handled in an inert, dry atmosphere of nitrogen or argon. Oxygen retards the effect of moisture and acts as a passivating agent. Plutonium reacts readily with oxygen, forming plutonium oxide and plutonium dioxide, as well as intermediate oxides. Plutonium oxide fills 40% more volume than the plutonium metal. It reacts with the halogens, giving rise to compounds such as plutonium X3, where X can be fluorine, chlorine, bromine, or iodine. Plutonium tetrafluoride is also seen. The following oxhalides are observed: PuOCl, PuOBr, and PuOI. It will react with carbon to form PuC, nitrogen to form PuN, and silicon to form PuSi2. Crucibles used to contain plutonium need to be able to withstand its strongly reducing properties. Refractory metals, such as tantalum and tungsten, along with the more stable oxides, borides, carbides, nitrides, and silicides, can tolerate this. Melting in an electric arc furnace can be used to produce small ingots of the metal without the need for a crucible. Plutonium can form alloys and intermediate compounds with most other metals. Exceptions include lithium, sodium, potassium, and rubidium of the alkali metals, and magnesium, calcium, strontium, and barium of the alkaline earth metals, and europium and ytterbium of the rare earth metals. Partial exceptions include the refractory metals chromium, molybdenum, niobium, tantalum, and tungsten, which are soluble in liquid plutonium, but insoluble or only slightly soluble in solid plutonium. Section 6.1, Occurrence. Trace amounts of 2 plutonium isotopes, plutonium-239 and plutonium-244, can be found in nature. Tiny amounts of plutonium-244 occur naturally because it is formed as a minor decay product in uranium ores, and it has a comparatively long half-life of about 80 million years. Even smaller traces of plutonium-239, a few parts per trillion, and its decay products are naturally found in some concentrated ores of uranium, such as the natural nuclear fission reactor and Oklo-Gabon. The ratio of plutonium-239 to uranium at the Cigar Lake Mine uranium deposit ranges from 2.4 times 10 to the negative 12th to 44 times 10 to the negative 12th. Minute traces can be found in the human body due to the 550 above-ground nuclear tests which have been performed and several major nuclear accidents. Most atmospheric nuclear testing was stopped in 1963 by the Limited Test Ban Treaty, but France continued to test into the 1980s, and several other nations also conducted tests after 1963. Because it is specifically manufactured and is the result of radioactive decay of uranium ores, plutonium-239 is the most abundant isotope of plutonium. Section 2. History. Section 2.1. Discovery. Enrico Fermi and a team of scientists at the University of Rome reported that they had discovered element 94 in 1934. Fermi called the element Hesperium and mentioned it in his Nobel lecture in 1938. However, the sample was actually a mixture of barium, krypton, and other elements, but this was not known at the time because nuclear fission had not been discovered yet. Plutonium, specifically plutonium-238, was first produced and isolated on December 14, 1940, and chemically identified on February 23, 1941, by Dr. Glenn T. Seaborg, Edwin M. McMillan, J. W. Kennedy, Z. M. Tatum, and A. C. Wall by deuterium bombardment of uranium in the 60-inch or 150-centimeter cyclotron at the University of California, Berkeley. In the 1940 experiment, Neptunium-238 was created directly by the bombardment, but decayed by beta emission 2 days later, which indicated the formation of element 94. A paper documenting the discovery was prepared by the team and sent to the journal Physical Review in March 1941. The paper was withdrawn before publication after the discovery that an isotope of the new element, plutonium-239, could undergo nuclear fission in a way that might be useful in an atomic bomb. Publication was delayed until a year after the end of World War II due to security concerns. Edwin McMillan had recently named the first transuranium element after the planet Neptune, and suggested that element 94, being the next element in the series, be named for what was then considered the next planet, Pluto. Seaborg originally considered the name Plutium, but later thought that it did not sound as good as plutonium. He chose the letters Pu as a joke, which passed without notice into the periodic table. Alternate names considered by Seaborg and others were ultimum or extremium because of the now discredited theory that they had found the last possible element on the periodic table. Section 2.2. Early Research. The basic chemistry of plutonium was found to resemble uranium after a few months of initial study. Early research was continued at the secret metallurgical laboratory of the University of Chicago. On August 18, 1942, a trace quantity of this element was isolated and measured for the first time. About 50 micrograms of plutonium-239 combined with uranium and fission products was produced, and only about 1 microgram was isolated. This procedure enabled chemists to determine the new element's atomic weight. In November 1943, some plutonium trifluoride was reduced to create the first sample of plutonium metal, a few micrograms of metallic beads. Enough plutonium was produced to make it the first synthetically made element to be visible with the unaided eye. The nuclear properties of plutonium-239 were also studied. Researchers found that when it is hit by a neutron, it breaks apart, or fissions, by releasing more neutrons and energy. These neutrons can hit other atoms of plutonium-239, and so on, in an exponentially fast chain reaction. This can result in an explosion large enough to destroy a city if enough of the isotope is concentrated to form a critical mass. Section 2.3, Production during the Manhattan Project. During World War II, the U.S. government established the Manhattan Project, which was tasked with developing an atomic bomb. 3 primary research and production sites of the project were the plutonium production facility at what is now the Hanford site, the uranium enrichment facilities at Oak Ridge, Tennessee, and the Weapons Research and Design Laboratory, now known as Los Alamos National Laboratory. The first production reactor that made plutonium-239 was the X-10 graphite reactor. It went online in 1943 and was built at a facility in Oak Ridge that later became the Oak Ridge National Laboratory. On April 5, 1944, Emilio Segre at Los Alamos received the first sample of reactor-produced plutonium from Oak Ridge. Within 10 days, he discovered that reactor-bred plutonium had a higher concentration of the isotope plutonium-240 than cyclotron-produced plutonium. Plutonium-240 has a high spontaneous fission rate, raising the overall background neutron level of the plutonium sample. The original gun-type plutonium weapon, codenamed Thin Man, had to be abandoned as a result. The increased number of spontaneous neutrons meant that nuclear pre-detonation, a fizzle, would be likely. The entire plutonium weapon design effort at Los Alamos was soon changed to the more complicated implosion device, codenamed Fat Man. With an implosion weapon, a solid sphere of plutonium is compressed to a high density with explosive lenses, a technically more daunting task than the simple gun-type design, but necessary in order to use plutonium for weapons purposes. Enriched uranium, by contrast, can be used with either method. The construction of the Hanford B reactor, the first industrial-sized nuclear reactor for the purposes of material production, was completed in March 1945. B reactor produced the fissile material for the plutonium weapons used during World War II. B, D, and F were the initial reactors built at Hanford, and 6 additional plutonium-producing reactors were later built at the site. In 2004, a safe was discovered during excavations of a burial trench at the Hanford nuclear site. Inside the safe were various items, including a large glass bottle containing a whitish slurry which was subsequently identified as the oldest sample of weapons-grade plutonium known to exist. Isotope analysis by Pacific Northwest National Laboratory indicated that the plutonium in the bottle was manufactured in the X-10 reactor at Oak Ridge during 1944. Section 2.4, Trinity and Fat Man atomic bombs. The first atomic bomb test, codenamed Trinity, was detonated on July 16, 1945, near Alamogordo, New Mexico, used plutonium as its fissile material. The implosion design of the gadget, as the Trinity device was codenamed, used conventional explosive lenses to compress a sphere of plutonium into a supercritical mass, which was simultaneously showered with neutrons from an initiator made of polonium and beryllium. Together, these ensured a runaway chain reaction and explosion. The overall weapon weighed over 4 tons, although it used just 6.2 kilograms of plutonium in its core. About 20% of the plutonium used in the Trinity weapon underwent fission, resulting in an explosion with an energy equivalent to approximately 20,000 tons of TNT. An identical design was used in the Fat Man atomic bomb dropped on Nagasaki, Japan, on August 9, 1945, killing 70,000 people and wounding another 100,000. The little boy bomb dropped on Hiroshima 3 days earlier used uranium-235, not plutonium. Japan capitulated on August 15th to General Douglas MacArthur, effectively ending the war. Only after the announcement of the first atomic bombs was the existence of the plutonium made public. Section 2.5 Cold War Use and Waste. Large stockpiles of weapons-grade plutonium were built up by both the Soviet Union and the United States during the Cold War. The U.S. reactors at Hanford and the Savannah River site in South Carolina produced 103 tons, and an estimated 170 tons of military-grade plutonium was produced in Russia. Each year, about 20 tons of the element is still produced as a byproduct of the nuclear power industry. As much as 1,000 tons of plutonium may be in storage, with more than 200 tons of that either inside or extracted from nuclear weapons. Since the end of the Cold War, these stockpiles have become a focus of nuclear proliferation concerns. In the U.S., some plutonium extracted from dismantled nuclear weapons is melted to form glass logs of plutonium oxide that weigh 2 tons. The gas is made of borosilicates mixed with cadmium and gadolinium. These logs are planned to be encased in stainless steel and stored as much as 4 kilometers underground in boreholes that will be backfilled with concrete. As of 2008, the only facility in the U.S. that is scheduled to store plutonium in this way is the Yucca Mountain Nuclear Waste Repository, which is about 100 miles or 160 kilometers northeast of Las Vegas, Nevada. Local and state opposition to this plan has delayed efforts to store nuclear waste at Yucca Mountain. Section 2.6 Medical Experimentation. See also the main article, Human Radiation Experiments. During and after the end of World War II, scientists working on the Manhattan Project and other nuclear weapons research projects conducted studies of the effects of plutonium on laboratory animals and human subjects. Animal studies found that a few milligrams of plutonium per kilogram of tissue is a lethal dose. In the case of human subjects, this involved injecting solutions containing, typically, 5 micrograms of plutonium into hospital patients thought to be either terminally ill or to have a life expectancy of less than 10 years, either due to age or chronic disease condition. This was reduced to 1 microgram after July 1945, after animal studies found that the way plutonium distributed itself in bones was more dangerous than radium. 18 human test subjects were injected with plutonium without informed consent. The tests were used to create diagnostic tools to determine the uptake of plutonium in the body in order to develop safety standards for working with plutonium. The episode is now considered to be a serious breach of medical ethics and of the Hippocratic Oath. More sympathetic commentators have noted that while it was definitely a breach in trust and ethics, quote, the effects of the plutonium injections were not as damaging to the subjects as the early news reports painted, nor were they so inconsequential as many scientists, then and now, believe. Unquote. Section 3. Applications. Section 3.1. Explosives. The isotope of plutonium-239 is a key fissile component in nuclear weapons, due to its ease of fission and availability. Encasing the bomb's sphere of plutonium in a tamper, an optional layer of dense material, decreases the amount of plutonium needed to reach critical mass by reflecting escaping neutrons back into the plutonium core. This reduces the amount of plutonium needed to reach criticality from 16 kilograms to 10 kilograms, which is a sphere with a diameter of 10 centimeters, This critical mass is about a third of that for uranium-235. The Fat Man-type plutonium bombs produced during the Manhattan Project used explosive compression of plutonium to obtain significantly higher densities than normal, combined with a central neutron source to begin the reaction and increase efficiency. Thus, only 6.2 kilograms of plutonium was needed for an explosive yield equivalent to 20 kilotons of TNT. See also nuclear weapon design. Hypothetically, as little as 4 kilograms of plutonium, and maybe even less, could be used to make a single atomic bomb using very sophisticated assembly designs. Section 3.2 Use of nuclear waste. PureX, plutonium-uranium extraction, reprocesses spent nuclear fuel to extract uranium and plutonium to form a mixed oxide, or MOX, fuel for reuse in nuclear reactors. Weapons-grade plutonium can be added to the fuel mix. MOX fuel is used in light water reactors and consists of 60 kilograms of plutonium per ton of fuel. After 4 years, 3/4 of the plutonium is burned or turned into other elements. Breeder reactors are specifically designed to create more fissionable material than they consume. MOX fuel has been in use since the 1980s and is widely used in Europe. In September 2000, the United States and the Russian Federation signed a plutonium management and disposition agreement, by which each agreed to dispose of 34 tons of weapon-grade plutonium. The U.S. Department of Energy plans to dispose 34 tons of weapon-grade plutonium in the United States before the end of 2019, by converting the plutonium into a MOX fuel to be used in commercial nuclear power reactors. Efficiencies are also attained through reprocessing. A fuel rod is reprocessed after 3 years of use to remove waste products, which by then account for 3% of the total weight of the rods. Any uranium or plutonium isotopes produced during those 3 years are left, and the rod goes back into production. However, the presence of up to 1% gallium per mass in weapon-grade plutonium has the potential to interfere with long-term operation of a light water reactor. Americium-241 has recently been suggested for use as a denaturing agent in plutonium reactor fuel rods to render the fuel unusable for conversion to nuclear weapons. Section 3.3 Power and Heat Source. The isotope plutonium-238 has a half-life of 87.5 years. It emits a large amount of thermal energy, with low levels of both gamma rays or particles and spontaneous neutron rays or particles. Being an alpha emitter, it combines high energy radiation with low penetration and thereby requires minimal shielding. A sheet of paper can be used to shield against the alpha particles emitted by plutonium-238, while 1 kilogram of the isotope can generate 22 million kilowatt-hours of heat energy. These characteristics make it well suited for electrical power generation for devices which must function without direct maintenance for timescales approximating a human lifetime. It is therefore used in radioisotope thermoelectric generators and radioisotope heater units, such as those in the Cassini, Voyager, and New Horizons space probes. Earlier versions of the same technology power the ALSEP and EOSEP systems, including seismic experiments on the Apollo 14 moon mission. Plutonium-238 has also been used successfully to power artificial heart pacemakers to reduce the risk of repeated surgery. It has been largely replaced by lithium-based primary cells, but as of 2003, there were somewhere between 50 and 100 plutonium-powered pacemakers still implanted and functioning in living patients. Plutonium-238 was studied as a way to provide supplemental heat to scuba diving. Plutonium-238, mixed with beryllium, is used to generate neutrons for research purposes. Section 4. Precautions. See also the main article, Plutonium in the Environment. Section 4.1, Toxicity. Isotopes and compounds of plutonium are toxic to highly toxic due to their radioactivity. Contamination by plutonium oxide, spontaneously oxidized plutonium, has resulted from a number of military nuclear accidents where nuclear weapons have burned. However, based on chemical toxicity alone, the element is less dangerous than arsenic or cyanide, and about the same as caffeine. Plutonium is more dangerous when inhaled than ingested. The risk of lung cancer increases once the total dose equivalent of inhaled radiation exceeds 400 millisieverts. The U.S. Department of Energy estimates that the lifetime cancer risk for inhaling 5,000 plutonium particles, each about 3 microns wide, to be 1% over the background U.S. average. It is not absorbed into the body efficiently when ingested. Only 0.04% of plutonium oxide is absorbed after ingestion. When plutonium is absorbed into the body, it is excreted very slowly, with a biological half-life of 200 years. Plutonium has a metallic taste. The alpha radiation plutonium emits does not penetrate the skin, but can irradiate internal organs when plutonium is inhaled or ingested. Particularly at risk is the skeleton, where it is likely to be absorbed by the bone surface, and the liver, where it collects and becomes concentrated. Considerably larger amounts may cause acute radiation poisoning and death if ingested or inhaled. However, no human is known to have died because of inhaling or ingesting plutonium, and many people have measurable amounts of plutonium in their bodies. Section 4.2, Criticality Potential. Toxicity issues aside, care must be taken to avoid the accumulation of amounts of plutonium which approach critical mass, particularly because plutonium's critical mass is only a third of that of uranium-235. A critical mass of plutonium emits lethal amounts of neutrons and gamma rays. Plutonium in solution is more likely to form a critical mass than the solid form due to moderation by the hydrogen in the water. Criticality accidents have occurred in the past, some of them with lethal consequences. Careless handling of tungsten carbide bricks around a 6.2 kilogram plutonium sphere resulted in a fatal dose of radiation at Los Alamos on August 21, 1945, when scientist Harry K. Dolligan, Jr. received a dose estimated to be 5.1 sievert, or 510 rems, and died 28 days later. 9 months later, another Los Alamos scientist, Louis Slotin, died from a similar accident involving a beryllium reflector and the same plutonium core, the so-called demon core, that had previously claimed the life of Dolligan. These incidents were fictionalized in the 1989 film Fat Man and Little Boy. In December 1958, during a process of purifying plutonium at Los Alamos, a critical mass was formed in a mixing vessel, which resulted in the death of a crane operator. Other nuclear accidents have occurred in the Soviet Union, Japan, and many other countries. Section 4.3, Flammability. Metallic plutonium is also a fire hazard, especially if the material is finely divided. It reacts chemically with oxygen and water, which may result in an accumulation of plutonium hydride, a pyrophoric substance, that is, a material that will ignite in air at room temperature. Plutonium expands up to 70% in volume as it oxidizes, and thus may break its container. The radioactivity of the burning material is an additional hazard. Magnesium oxide sand is probably the most effective material for extinguishing a plutonium fire. It cools the burning material, acting as a heat sink, and also blocks off oxygen. To avoid these problems, special precautions are necessary to store or handle plutonium in any form. Generally, a dry, inert gas atmosphere is required.